Hello everyone, we are from Group 2 and today we will be discussing the different types of catalysts and their respective modes of action. First and foremost, there are two types of catalysts, heterogeneous and homogeneous.
A heterogeneous catalyst is a catalyst that is in different phase as the reaction mixture. Reactions catalyzed by a heterogeneous catalyst commonly involve gaseous molecules reacting at the surface of the catalyst. There are three main steps involved in the mode of action of a heterogeneous catalyst, namely adsorption, reaction, and desorption. We will also look into a few examples which include iron as a catalyst in the Haber process, and also palladium, platinum, and rhodium found in the catalytic converters of cars.
Let's first take a look at how iron acts as a heterogeneous catalyst in the Haber process. Iron is a solid in this process, while the reactants, nitrogen and hydrogen, are gases. Therefore, it is evident that the catalyst is in a different phase from the reactants, thus making it a heterogeneous catalyst. As you can see on the left side of the screen, nitrogen and hydrogen gases diffuse the surface of the iron catalyst. Afterwards, absorption occurs wherein the reactants form bonds with the catalyst, which causes the pre-existing bonds in the reactants to be weakened. Henceforth, the hydrogen atoms and the nitrogen atoms are able to react together to form ammonia. It is worth noting, however, that the bonds that were formed between the reactants and the catalyst previously during absorption are weak enough to be broken. This is how desorption is able to take place, and during this process, the bonds between the products and the catalyst weaken and the products are released. Afterwards, ammonia diffuses away from the surface of the iron. Now let's take a look at the rest of the screen. Palladium, platinum, and rhodium also have similar modes of actions as iron does in the Haber process. Car exhausts are oftentimes fitted with catalytic converters, which makes use of the three aforementioned metals as catalysts. These catalytic converters have a honeycomb structure similar to what you're seeing on the screen right now. And this structure consists of small beads called platinum, palladium, or rhodium. As the nitrogen oxide and carbon monoxide are absorbed onto the surface of the catalyst, the weakening of bonds within the reactants occur, and this allows adjacent nitrogen atoms to form new bonds with each other. And similarly, carbon monoxide and oxygen atoms form new bonds with each other as well. Henceforth, nitrogen and carbon dioxide are produced, and they proceed to undergo desorption, which allows them to leave the surface of the catalyst. The two equations for the overall reaction for this process is shown on the screen, where the first reaction involves nitrogen monoxide, and the second involves nitrogen dioxide instead.
Next, let's move on to homogeneous catalysts. These catalysts are in the same phase as the reaction mixture. Oftentimes, changes in oxidation number of the ions involved in the catalysis occurs as the catalyst undergoes electron exchange with the rest of the reactants. This is also why transition elements often make good catalysts, as most of them have the ability to change oxidation numbers. Two different examples of homogeneous catalysts include atmospheric oxides of nitrogen, which are involved in the oxidation of atmospheric sulfur dioxide, and also Fe3+ or Fe2+ ions that catalyze the reaction between iodide ions and peroxodisulfate ions.
As you can see, sulfur dioxide is being oxidized into sulfur trioxide in the overall reaction. However, the complete catalyst of the oxidation of sulfur trioxide actually involves two steps. First, the nitrogen dioxide present in the atmosphere reacts with sulfur dioxide to form sulfur trioxide and nitrogen monoxide. At this stage, nitrogen undergoes a change in oxidation number from +4 to +2, while the change in oxidation number of sulfur is from +4 to +6. Next, the nitrogen monoxide proceeds to react with the oxygen in the atmosphere, and thus the nitrogen dioxide is reformed. This is the common mode of the action of homogeneous catalysts. They are often used up in one step but later on reformed again.
For the second example, we have once again a two-step reaction for the catalysis of the reaction between iodide ions and peroxodisulfate ions. There are two possible methods in which the reaction could go on. The first being Fe3+ ions oxidizing iodide ions and forming iodine and Fe2+ ions, after which the Fe2+ ions will react with the peroxodisulfate ions to reform the Fe3+ ions and form sulfate ions. The second method would be what you are seeing on the bottom right on the screen, which is the Fe2+ ions reacting with the peroxodisulfate ions first to form Fe3+ ions and sulfate ions, which will be followed by the Fe3+ ions reacting with the iodide ions to form iodine and reform the Fe2+ ions. This simply shows how the order of the reaction does not matter in this case. In addition, as you See on the graph situated on the bottom left of the page, the activation energy is lowered from the one where a catalyst was not used, and it is also seen as two humps. This occurs because the reaction was a two-step process.
To summarize, catalysts are used to lower the activation energy of reactions by providing an alternative pathway with lower activation energy. There are two different types of catalysts, namely homogeneous and heterogeneous, where the phase of the catalyst is the same as the reactant for homogeneous catalysts and different for heterogeneous catalysts. Homogeneous catalysts are often used up, then reformed later on, while heterogeneous catalysts involve processes such as adsorption and desorption. That is all for today's discussion. Thanks for watching!